In this video, we'll be discussing the various gas laws. The first law which was given is Boyle's law. It was given by Robert Boyle in 1662. He said, temperature remaining constant, the volume of given mass of a gas is inversely proportional to its pressure. So Boyle's law says, or Boyle's law is the relationship between volume and pressure at constant temperature, and actually all the laws are given for a given quantity of a gas. So according to Boyle's law, V is inversely proportional to pressure, or we can write PV is equal to constant at constant temperature. This can also be studied as temperature remaining constant, the product of pressure and volume of a given mass of a gas is constant. Suppose P1 is the pressure and V1 is the volume, that is initial pressure and initial volume of a gas at constant temperature, which changes to P2 and V2, the final pressure and volume. Then according to Boyle's law, P1 V1 is equal to P2 V2. So this is required for solving numericals. So out of these four, any three will be known and one can be calculated. Now let us learn some of the graph based on Boyle's law. So we can have different graph or plots based on Boyle's law. We can have P versus 1 by V. We can have P versus V. We can have PV versus P or V. One more graph can be obtained by taking this relationship. So taking log both sides, we can write log P plus log V is equal to constant, or log P equal to minus log V plus constant. So here this equation is in the form of equation for a straight line, that is y equal to mx plus c, where m is the slope and can be compared with this. So y is log p. Along x-axis we can take v, log v, and the slope comes out as -1. That is, this is equation for a straight line having negative slope. So we can have the graph one by one. So first, pressure versus 1 by V. So it is direct relationship. So we can take like this. Pressure 1 by V. As it is directly proportional, it is a straight line passing through the origin. That means P increases, 1 by V also increases. Next, when we want to plot a graph between P versus V, we get rectangular hyperbola. One increases, other one decreases. This is a graph between P and V at constant temperature, and it is also called as isotherm. Now the third graph, PV versus P, is a straight line parallel to any of the axes, depending upon on which axis you have taken PV. So suppose PV is taken along y-axis and P is taken along x-axis. So equate the curve or the plot will come as a parallel line to the x-axis. Now, when we want to plot a graph by taking the log, that is log P equal to minus log V plus constant. So this side obviously log P will be taken y, and this side will take log V, and then negative slope will get a curve like this. Next law is Charles' law. So Charles' law says pressure remaining constant. Pressure is constant. Pressure remaining constant, the volume of a given mass of a gas increases or decreases by 1 by 273 of its volume at 0 degrees Celsius for every 1 degree Celsius rise or fall of temperature. It says that pressure is constant and the volume of a gas increases or decreases. That means temperature increases, volume increases. Temperature decreases, volume decreases. But there is a value or there is a relationship between how much of the volume decreases or increases. Then it is given in the Charles law. It is 1 by 273 of its volume at 0 degrees Celsius. So mathematically we can give like this. Suppose V0 is the volume at 0 degree Celsius. So V1 at 1 degree Celsius, V2 at 2 degrees Celsius. So mathematically we can derive the Charles law like this. So we can write V1 is equal to V0 plus V0 into 1, this is degree centigrade, divided by 273. Similarly, at 2 degrees Celsius, we will have V2 as the volume. So it will be V0 plus V0 into 2 by 273. Similarly, at T T degrees Celsius, that is small t degrees Celsius, will have V0 plus V0T by 273. Or we can write it as V0 1 plus T by 273. Or this is equal to V0 273 plus T degree centigrade, we can write by 273. 273 can also be written as plus 0 degree centigrade. So we can write here again Vt, V0. Let us take small t degree Celsius plus 273 as capital T. At small t degree Celsius by capital T at 0 degrees Celsius. So we can put it together. V0 by T0 equal to Vt by Tt. Or we can give it as V by T is equal to constant. Now here we have taken capital Tt is equal to 273 plus T degrees Celsius. Here we define or we introduce another scale of temperature, that is Kelvin scale of temperature or absolute scale of temperature, where we add 273 to degree centigrade through the temperature in degree centigrade to get the temperature in Kelvin scale of temperature. Now V by T is equal to constant, or capital V or volume is directly proportional to the Kelvin scale of temperature. We started with the temperature in degree centigrade and we reached the temperature in Kelvin scale. Now we can plot the graph. Similarly, as we have derived all this for the increase in temperature, so for decrease in temperature it will be V minus 1 equal to V0 minus V0 by 273 because minus 1. Similarly, V minus T will be V0 minus Vt into V0 by 273. So Charles' law gives the variation of volume with increase and also with decrease of temperature. Now for the graph, we require at least 3 points to be plotted. Now at 0 degrees Celsius, we have the volume as V0. At 273 degrees Celsius, the volume will be, here you see, 273 plus 273 will give you 2 into 273. So 273 cancels and we get 2V0. So it will be double the volume at 0 degree Celsius. Now at minus 273 degrees Celsius, volume will be 0. So we'll take the graph. This is the origin, or we can take the temperature in degree centigrade. So along this direction we'll take volume. So this is 0 degrees centigrade. So at this temperature let the volume be V naught. So this is one of the points. And suppose this is minus 273 and this is plus 273 degrees centigrade. So at minus 273 degrees centigrade, we have the volume as 0. So here comes the point. And then plus 273, it is 2V0. So approximately here. We can join the 3. So we can find that at minus 273 degrees Celsius, the volume becomes 0, and below this temperature, the volume becomes negative, which is actually not possible, or such temperature is not possible where the volume will be 0 or it will come as negative. So this temperature at which volume is supposed to be 0 or the volume ceases is called as absolute 0. In fact, no one has ever traced this contraction in volume. Volume can never be 0, it cannot be negative. So this is the graph at constant pressure. So at constant pressure, the graph what we obtain between the volume and temperature are called as isobar. So we can define absolute 0 like this. The lowest possible hypothetical or theoretical temperature is minus 273 degrees Celsius, at which a gas is supposed to have, not possible actually, supposed to have 0 volume. And this temperature is called as absolute 0. Actually, the exact value of absolute 0 is minus 273.15 degree Celsius. So, if we want this, we have already learned. If we want to change the temperature in Kelvin scale from degree centigrade, we can add 273 to the temperature in degree centigrade. So for numerical purpose, we can have the equation V1 by T1 equal to V2 by T2. We derived as V0 by T0 equal to Vt by Tt. So we can have also V1 by T1 is equal to V2 by Tt. Next comes Avogadro's law. So Avogadro's law is very simple. It says, this you might have done earlier also, equal volumes of all gases contain equal number of molecules under similar conditions of temperature and pressure. So we can write V directly proportional to small n, where n is the number of moles of the gas. So it says under similar conditions of temperature and pressure. So we can define here STP, standard temperature pressure. So standard temperature pressure is 0 degree centigrade, or this is equal